let's continue with the OS dev here. I have a test build of the OS that I was messing with before I did these recordings. The actual changes I'm going to be making will be slightly different from what I did here. This is just, a test example, but this is running in a video mode from Vesa Bios Extensions. This is 800 by 600, 32 bits per pixel. For the actual OS, I'm thinking 1920 by 1080, 32 bits per pixel if it's not too slow performance-wise and everything. Maybe it's hard to tell, but this is different than it used to be. It's a custom bitmap font that I have in a font file that I did here, so FNT. I have a second stage bootloader that I move the global descriptor table and the new Vesa Bios extension code into, and then printing and everything is just the same. So this video will probably be over adding the Vesa Bios extension code to the bootloader, well, to a second stage bootloader that is loaded from the bootsector. The second stage loads the kernel and everything as we normally are doing. Text mode doesn't work, so printing had to change, so I'll probably show how to make a custom bitmap font as well. So hopefully this doesn't take too long, but we'll see. If you want a little taste of the font, I just had it here. It's, when I say bitmapped, I mean literally, a bunch of zeros until we get to visible ASCII characters. Here's ASCII, 33? That's the exclamation mark. It's hard to see, but there's, ones here where I want the pixels to be drawn and zeros otherwise. So I can go to the bottom as well. It's a pretty big file. I'm doing an 8 by 16 font here, so 1 byte is 8 bits. And you can just read it bit by bit, and if the bit is set, we want to draw a pixel. If it's not, we don't. It's pretty simple. So it's 16 bytes. Each byte is 8 bits. If there's a 1, we draw a pixel. Here's a left curly brace, so the ones kind of follow the pattern. And we got the curly brace here. So that works pretty well. And it's really not that bad. It's pretty simple. Second stage bootloader that I'll be showing in a minute. I moved the VBE code into. We'll go over that, but it's really you're just setting up data structures and some basic function calls like we've done for BIOS stuff in the past. Just for, video mode. So where 4F01 gets the mode info, 4F02 sets the mode, and 4F by itself calls and gets the info overall, but we'll get to that in a second. So first I kind of want to go over Vesa Bios Extensions itself, which is what I'm going to be moving towards. This is the Wikipedia page over Vesa Bios Extensions. I'm just showing this because I got the link for the standard here, Vesa Bios Extensions 3.0, newer processors, newer computers. Since this is from 1998, newer computers use UEFI. I'm not doing UEFI at the moment because it's a bit more involved than what I've been doing. But if you want to, do stuff the older way still, well, it's still supported for now. Here you go. This is from that link. Vesa Bios Extensions. Vesa stands for Video Electronics Standards Association. BIOS, again, I don't know, basic input-output system. And we'll just be using a couple of the functions here. Okay, function reference. So call these from real mode, not protected mode. So the reason I need a second stage bootloader is because one 512 byte sector does not hold enough code for BBE and the global descriptor table and our other code that we're loading stuff from. If we didn't load everything within the boot sector, we could probably fit all this into the boot sector, but the second stage is fine. It's just loading and jumping to another place. But we do this within real mode. The software interrupt 10 for the BIOS video services is what was appropriated for this. That's kind of why they're BIOS extensions. So 4F goes into AH for all of these. AL indicates sort of which function you're using for the overall 4F VBE functions. We're basically just using 4F, 4F01, and 4F02. So AL 0, 1, and 2 respectively. This explains how the numbers are set, how the bits are set. There are built-in VBE graphics modes that you can try and use, and they may or may not be supported. They're not guaranteed to be supported ever, starting with 2.0. They didn't define any new ones, and starting with 3.0, these really aren't guaranteed to be there. You should call a function to get the list of supported modes, which is what we're going to be doing. And then you query each mode for the info associated with it. And if it's the one you're looking for, then, you're good to go. There's a lot more explanation in here for stuff that I'm not going to be doing. Return controller info. So this gives you basically a big info block structure with pointers to areas of memory that says, hey, look in here for the supported video modes for your setup. So AX 4F00, so AL is 0, AH is 4F. ESDI is a pointer to the buffer where you want to put this stuff, so you can declare it in memory and just point to there. I have this set up in code, I'll show that here. In my example, second stage, I will be putting this in the regular OS, but I'll show how it's set up first. So VB info block, I have this set up like they have it, with the signature as a byte, you know, the version, which I'm not setting. In the document it says this is set to 0300 and hex for version 3, but I'm not doing that. So the video mode pointer is what we're going to be using. We're going to be querying that. I set that up with a segment and offset, and I use that to find the mode. So basically I'm just querying that area in memory. It is defined in the standard that the end of the modes, it gives you a list of modes in that area in memory, and if you're at the end of the list you'll read FFFF, so before that point you can keep reading and see if you're at where you want to be. Otherwise you can keep getting info for those modes. So basic high level explanation, I'm just getting the mode with 4F02, checking the XY in bits per pixel. If it's not equal, I'm getting the next one. So that's all I'm really doing here, but we have the data structures set up in memory is all it's trying to show there. List of mode numbers. Each mode number is one word, so you read 16 bits at a time. And it's terminated by -1 or 4 Fs in hex. It gives you the list of the potentially supported modes. Generally they are supported, at least in QEMU they're all supported, but they might not be on your specific hardware. VBE2 is present or statically stored. We are using VBE2. Yeah, so if you want to use modern by VBE standards, all the stuff available, put VBE2 in the signature area. But we're also, really what we're using is 4F01 and 4F02. 4F01 returns the mode info for the mode that you select, so you read 16 bits at a time from that mode pointer that we got in the first, VBE info block. You just put that's pointed to by ESDI from the first function. So you read 16 bytes from that. You get a mode, you read the info for that mode after you do this. So we have a pointer to a mode info block structure. And that is also down here, mode info block right here. Starts there, mode attributes. And this is defined within the standard, but all this stuff, all I'm really cared about with this is bytes per scan line, or alternatively linear bytes per scan line if we want to do a linear frame buffer, which we do want to do, because it's easier to work with than bank switching or other things. Or windows like they have here, we don't need to worry about that. All I'm really doing right now is checking the bytes per scan line, checking the X resolution, the Y resolution, and the bits per pixel. So X, Y, and bits per pixel, my example, 800 by 600 pixels and 32 bits per pixel. So each pixel is 4 bytes in ARGB colors. You will have to mess with the red, blue, green masks and field positions, I guess if you have a YUV or direct color memory model, but I haven't had to deal with that yet. We also need the physical base pointer primarily, because this tells us where the linear frame buffer is at in memory. And usually for this, at least in QEMU, it usually defines somewhere between like 3 and 4 gigs. So what's called high memory is where this is going to be. So instead of, like we have been using text mode B8000 or VGA graphics mode at A000 hex, both in hex, those memory addresses were for text mode memory, or color text mode memory rather, and then graphics mode memory. Here, we're going to be using whatever is returned within the physical base pointer in this mode info block, and that tells us where we can write to draw to the screen. So that's what we'll be using. Okay, let's do 4F. I'll look at this stuff again. So the first thing, function that was defined, set up the VB info structure. So AX0 ESDI points to the VB info block that we have set up. 4F and then 00 and AL for the function. That returns everything within the VB info block because we said we want to point to there. Taking the pointer, getting an offset and a segment. The reason I'm doing T segment is because the word segment is a keyword within FASM. So I couldn't use that, so I just underscore it with the T for some reason. I don't know why. Offset, so pointer and pointer plus 2. I'm just going to be moving up 2 bytes at a time, 16 bits at a time to check each mode. That's all this is doing, is setting up that code. So I'm using FSSI. The reason I'm using this code specifically is because there were examples on OS Dev Wiki. So this is kind of just following those. There's like a Vesa tutorial that I kind of got this from, I think. Increment by 2 bytes to set up for the next mode is all this is doing. I'm getting the first mode first. I'm checking if we're at the end of the list. If not, then we're not. Otherwise, we're getting the info for that mode. So since I moved the mode number into a mode, sort of variable, moving that to CX, defined by the VBE function here, 4F01. On return, AX should be 4F00 whenever any of these functions return. If it's not, then we had an error, so that's why I keep checking for this. 4F01, we send it the mode info block data structure and ESDI. ES was set to 0 above, that's why I'm not setting it here. And that gives us the info that fills out everything down here because we said we want to point to here. So after using 4F01 on whatever a current mode we're checking is, I'm just checking for the X and Y resolution and the bits per pixel right here. So I'm saying, hey, we got the X resolution from this function up here. Now I'm just printing it right here. I'm printing it out to the screen. Down here, I don't have to do this. This isn't affecting what I'm doing now, but for debugging, that was pretty useful. But here I'm actually checking it. So I'm saying I set a value down here called, let me just open it on the other side. Yeah, I set my values down here for width and height. So I was doing 1920 by 1080, which also works, but for simplicity's sake right now, 800 by 600, 32 bits per pixel. So the width 800, does it equal the width that we got returned for the current mode that we're checking? If not, we go to the next mode. So the height as well. If it's not 800 or not 600 or the bits per pixel is not 32, then we're checking the next mode. If it is, we're going to set the mode. But the next one, I'm just moving these two kind of counter or interval sort of variables. And we go back up to find mode, which just gets the next mode number and checks again with the 4F01. So it's actually pretty simple code. But if everything was equal, we want to set the mode. So, okay, 4F02 and AH. Well, 4F and AH, 02 and AL, AX, 4F02. Set the mode. If we find the mode number we want, then we put the mode number into BX. We can change some bits in there for flags. The one we're interested in is the linear flat frame buffer model. So this is bit 14 within the mode number in BX. We also set ESDI if we want to a CRTC info block structure. That's only if you're doing something that needs that. Like if you're setting bit 11, if you want to change the refresh rate, then you need this, but we're not doing that. But basically 4F02 and AX, BX is the mode number. If we want to set on bit 14 for the linear frame buffer, that's all we'll be doing here. So 4F02, move the mode number to BX, or it with 4000 in hex, which is bit 14. X4DI, call it with, because I'm not doing the CRTC microcontroller, I don't need to worry about it, I just XORed it. I don't have to do this, but I did it anyway. Compare. If we're all good, then we load the global descriptor in this example that I have. Here this is just printing out hex like I've done before, maybe slightly differently, but then yeah, in this example I have, the global descriptor table code that we did before. This is, where it's at now, along with the Vesa Bios extension code. Then we do the same thing I've done before, load the segments, set the drive number, which I might change how I do that. I'm storing the mode info block as well to some sort of global location, so I don't have to worry about where it's set up. It's stored. I can just read from this area in memory to know what values I have set, like for the X and Y resolution, bits per pixel, the bytes per line. That's all I'm doing here. The mode info block is 64 times 4 bytes long, so 256 bytes long. And I'm just moving string double word ES to DI, or SI to DI. And then jump into the kernel like I was doing before. So yeah, this mode info block down here, where I have sector 3, is 256 bytes long. So that didn't really explain too much, but that's what I'm doing with that. And then how I change, I'm going to type this all up in a second too, so I'm not really sure why I keep explaining this, but anyway. I'm trying to go over it. Second stage. So the only thing I changed in the bootsector for this example is I changed to load more things from disk to memory. So since I have a second stage bootloader, I'm loading that first. Since the bootsector is initially loaded to 7C00, I wanted the second stage to be right after the bootsector in memory, just I don't know, for reasons. So 7C00 in hex plus 512 bytes is at 7E00. Pretty easy enough. My second stage was 3 sectors. So just loading 3 sectors in memory, then, you know, same thing like we did before. We're doing the same sort of reading from the ATA PIO ports. File table is coming second. Kernel is coming third. These were originally first and second. Then since I made a bitmap font, I'm reading that into memory after those first 3 because I need a font to print stuff, print text. Bitmap text. The font that I showed briefly earlier is just loaded to 6,000. And it takes up 4 sectors. 8x16 font and sort of 127, 28 ASCII characters, although maybe I did 256 times 4 instead, but whatever it was, it took up 2,048 bytes, or 4 sectors, so that's why I'm loading that. And that's really all I'm doing in the boot sector now, is just loading everything and then jumping to the second stage down here with the far jump and saving the drive number. I'm probably going to change to just put the drive number somewhere in memory, like at 4,000 or something, some other 1,000 denominated memory address, just so I don't have to keep moving it into a register every time I like jump to another program or anything, because that's really annoying. I'll just have it at a set location in memory, and that'll make it easier to deal with, I think. But that's kind of all I'm doing there. There wasn't really too much in the kernel or anything. I mean, other than changes I had to make to print bitmap fonts, but that was more in the print functions. I'm just going to show this right quick before I actually implement it in the regular OS. Since I loaded everything to global location 5000, I can just read from that. So the mode info block was loaded to 5000 at the end of the second stage bootloader. The frame buffer address, the physical base pointer. The physical base pointer is basically 40 bytes into the VBE mode info block. So 40 in hex is 28. So 5028, you can just load double word value whenever you want to deal with the writing to the screen, whenever you want to deal with the frame buffer. The bytes per scan line basically says how many bytes are in one line. For this, it's simple. It's just the number of pixels times 4 because it's 32 bits per pixel. That's not guaranteed to always be true for every single mode. So it's helpful to use that instead, just in case the bytes don't, you know, line up exactly with the bits per pixel times the number of pixels in a line. That's not always guaranteed to be true. So I'm just reading it here just in case though. So I'm just showing that, yeah, I'm reading things from that global location we set up, and I changed printing just a little bit because we have different locations for the frame buffer, and since I'm using an 8x16 bitmap font, I have to kind of translate the character address on screen into, you know, where we need to print it. Line 1 in the screen, pixel line 1, is not going to be line 1 for like characters, since characters are 16 pixels high. In my font, I have to go down 16 lines for the next line of text that's going to be written, not line 2. That would look, you know, bad. So that's all that I like change stuff here. But anyway, I'm going to get to the regular OS. Sorry, if hopefully you weren't trying to type along or anything, because that wasn't the point. Just sort of brief high-level overview of what changed and what I'm going to be going over to get to something like this. Now, I will probably be doing 1920 by 1080. Although I forgot, but I remembered Control-Alt-F, if you're actually within focus in the QEMU window, will make it full screen. Stuff is a little slower. I mean, stuff still works, but also scrolling's slower than it normally is. Everything still works. I guess I can show that, you know, loading files still works, saving everything. I do still have a couple issues with leaving the underline there, which is my cursor position that I'm moving. I had a fun time debugging that for a bit, but other than it still left it there after I entered a command. Maybe I'll fix that up, but anyway, we'll be getting to this result. I just wanted you to see the font a little bit larger so it's easier to see. If that didn't blind you too much. If the font is too small, this 8x16 font, if this is too small in like 1080p resolution, then I'll increase the font size for another custom font. Like maybe I'll just double it to 16x32 or something. And then exit. Okay. Here in my OpenBSD, this font here is, I think, 18. I didn't want to do that. Let's go less. Yeah, Deja Vu Sans Mono. So 18. I'm using a regular 18 point font. So maybe I'll look for that. I'll make some 18 pixel wide or tall or whatever that means. Font, we'll see. Okay, now I'm in my regular OS here. Yep, all right. So in our regular OS, that has not changed. So this looks a little different. I might try and make a monospace font. I know the spacing between letters is called like kerning or something, right? And I don't really mess with that. But in the regular OS, see, we have a blinking cursor. In the new graphics mode, we won't. But everything should still work the same, if not a bit slower, because I'm doing a lot more operations for drawing the text, but that's okay. Okay, so let's set up basically our example that I just showed you briefly. Let's set that up in the actual OS and we'll get going here. So I want to load a second stage that I'm going to move the global descriptor table code and the new Vesa Bios extension code into. So let's just make a second stage bootloader file here. I'm going to put it in the source file where all the other stuff is. And I called it second stage. We can just keep that name, that's fine. I'll make second stage dot. I can probably be easier if I went to there first. Let's do the bootsector and the second stage. So let's do the big O. And we'll do that. So second stage bootloader. Second stage code is going to hold the GDT code, so it will start out in 16-bit. It'll change to 32-bit later, like how we're doing currently in the bootsector. And I'm going to start it at right after where the bootsector is loaded into memory to start off with. So this is going to be 512 bytes after 7C00, just because I think it lines up cool conceptually. So this will be 7E00. So what I'm going to do, I'm going to keep the sort of disk loading code within the bootsector, but the GDT I'm going to move. This load GDT label will have to change here. So I'll put this here so I don't forget. Change this label. All right. But the GDT here will go down, set segments. We'll just take all of this. Take all of that, put it over here. So instead of load GDT, I'll do, we'll say we'll jump to second stage bootloader here. And I will call it load second stage. This will end up jumping, I'll do a far jump. Although I'm not sure if I have to, but it was working, so I'll keep it because it was working. Do a far jump to 7E, which should jump to this place over here because it will be loaded starting at 7E. So this I'll change to load second stage. Get rid of that. Okay, so if we don't change anything else, this should still work normally. So let's just see if it does. Now it jumps to the kernel. Okay, well actually it won't because we need to add it into places. I'm going to add it to the file table as well, which means I'll have to change these values within the bootsector, but that's fine. I'll just add it here before I forget. So I called it second stage. It's not a comment. Called it second stage, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then 5, 6, 7, 8. Okay, so 2 blanks for 10. Make sure it lines up. It's the first thing. This will be now at sector 2 on the disk. It will be, ultimately it's going to be 3 sectors long, so I'll just put 3 there for now. So 1 plus 1 is 2 in hex, although it doesn't matter right here. But anyway, 2 plus 3 is 5. So 5 plus 14 is 19. So this should be a 3, right? And then that'll be 14 in hex. This will be 19. So that should be all right. So we'll have to change this. The file table now starts at 13. Yep, because we add the 3 for the second stage we just added. Yep, okay. And yeah, I will change this to read, I think, the second stage first. So I'll put that here. Read second stage bootloader into memory first. Let's set that up. To finish this part. This will be second for the file table. I'll probably just copy, no, this is just one sector. I'm going to be doing multiple. So I'll copy the kernel read code because that deals with multiple sectors. This will be third. So let me just copy this right here. Down to low, down to here. Okay. All right. So this will be reading 3 sectors. I know I didn't set it up to be 3, but we'll change that in a second. So I need to do -1, so that'll be 2. We'll be reading 3 sectors. Address to read into will be 7E00. So 7E00 and H. These are the same. Number of sectors read will be 3. Sector to start reading at will be 2. That's correct. Okay, this we're gonna call, I can't do that. I'll call it second, I don't know, second stage loop. Call it that. That's for 1. Okay, compare BL. Load second stage. That will change as well. Because that is the ending point, is what this was. Let's do load file table. So I'll make a label here. So it'll jump here when it's done reading. Load file table. Otherwise it'll go and read at second stage loop. Okay. So when load file table is done, it'll just go immediately onto the kernel, read that in. That'll go down to here, jump to the second stage. All right. So second stage at the bottom, I want it to be 3 sectors ultimately, so we'll do 3 sectors in length, which will be 1536 times 1536 minus the dollar minus dollar, get the current position, fill it with zeros. Sector padding, okay. So we got that there, all right. So now I want to load that in, so I'll change the makefile as well. I'll put it after the boot sector on the disk. It doesn't need to be boot sector, it needs to be second stage.bin. Okay, that should be all right. Now let's see what happens. Undefined symbol drive num. Is that in second? Yeah, it is. Do I load it in before? No, I don't. I guess we'll keep it here before we jump. Just to be consistent. So we'll put the drive number there as I saved it off to begin with. Okay. And then in here, the other one's drive num, so I think in the example I called it loader drive num. I'm going to change this, but I want everything to be the same first to make sure it works right. So I'll do this first, call it loader drive num. And before we actually jump to the kernel, I'll move it back before we set the segments, I guess. Loader drive num. Actually, I'll do it here. So it's accessible in the kernel with the same thing that we've been doing. Let's do variables or data area, whatever. It's loader drive num. And we'll set it to defined by 0. That one I put an underscore into it. Just get rid of that. And yeah, okay. Is that all right? No, undefined symbol. Oh, I still have drive num. Yeah, this needs to change. Loader drive num. Oh, I already moved it there. Yeah, I don't have to do that then. I should read my own code before I try to mess with it. All right, does this work or does it not work? It doesn't work. Well, that's good. Probably because the hard disk and everything, their positions changed, and I did not change that within the boot sector, right? That's probably why. I just realized that. So let's get that back over there. File table is, yeah, at 13. We're reading 1. The kernel is different. The kernel is still at E, but it starts at sector 5. Yeah. That's why. Kernel, sector 5, yeah, for 13. That would probably be the only issue there. It was actually not loaded to memory, which is not good. And it still doesn't like it. Well, that's nice. Cool, now I get to debug what's wrong. Oh, yeah. Because I'm doing this stuff. Yeah, that's probably not good. I need to jump there first if I'm doing this. That's executable. Let's jump to load GDT. The GDT itself is data. It is not executable memory. I could move it down into our data area section. That might make more sense, but I'm not. So yeah, we want to jump to that and actually run the code first, not try to load the GDT, which is not code. That may have been the issue. Yeah, that was the issue. Okay, so everything should work normally as it has been. We're just using a second stage bootloader like I have here as a little in between the boot sector and the kernel. Okay, so we'll just start with that. But that's how you get a basic second stage bootloader working. If you want to do stuff within here, you know, we're not beholden to one sector for our first booting code, really. All right, let's open up that other stuff that we had, and it is like way far back into here. Okay, go to source. All right, so this is the second stage bootloader code from my example that I showed. I just don't want to spend like 30 minutes typing all this out when I already have it working, you know, it's kind of a waste. So let's set this stuff up first. So I'm gonna copy, yeah, see, I called it loader drive. No, that's all right. I'll copy this. And that. So put that below here. So these are the variables I'm adding to our actual OS. This, like I'm typing hex, or like I'm printing hex in the regular OS, I just put a little subroutine into the second stage so I can print it out. That was for debugging. I don't really need this here, but I'll include it for the sake of completeness for my test in case you want to check values that you're getting, right? I'm not going to do 800 by 600. I will do 1920 by 1080 with height, BBP, bits per pixel, offset and segment. I did T segment just because segment is reserved in FASM. Name this whatever you want, but these are just going to hold the position for the video mode pointer, which is here within the VB info block. That's all that these are going to be used for in my code, and then mode is the mode number that we're going to be using. See, I might as well put this here. This is, okay, let's copy the VB info block and the mode info block. I'll put that over into my stuff. Okay, pad out the rest. All right. So I'll stop it here in case you need to type it out on your end, or maybe I'll provide the source code or something. But the VB info block that was defined in the, you know, in the standard, we have the VB signature, and it's easy to do these with dots, so you can just refer to VB info block dot, you know, video mode pointer. That's an easier way to refer to it with labels. But we have the, you know, the signature is 4 bytes. I just did define byte, but VBE2. The version, at least in QEMU, does not have to be set, but I mean, I could set it to 300. It didn't seem to change anything when I was testing. We'll just leave it at 0. This other stuff I'm not going to mess with. Video mode pointer we're going to use to get the mode numbers. But then you have total memory, OEM software revision, you know, OEM vendor name, product revision, and then reserve data. The standard has these reserve data, you know, 222 bytes and then 256. But I'm not doing that because I'm not an OEM and I don't care. And we have the mode info block after that, because this is, I believe, 512 bytes. Yeah, because we do this whole reserve thing. So this is technically sector 3. And this is sort of the end of sector 2 here. If I had the sector padding. Let me fix that first. That would be good. There we go. Yeah, now this is actually sector 2. Okay, and this is actually sector 3. Let me get rid of that. And after all that, it will be 3 sectors. That's why I had that specific padding. But let me go up here. The mode info block, after the VB info block that I'm using. The standard has these, so I just put the labels in because they were the same, or the comments in, just to match the standard. But mandatory info for everything. We have mode attributes, window A and B attributes, window granularity, window size, window A and B segments, window function pointer, and bytes per scan line. The only thing I'm using from this is the bytes per scan line value to get the number of bytes for one line in our actual screen. So if you want to go down one pixel line in the screen, you'll use this bytes per scan line value, or however many lines. If you want to go to the middle of the screen and you have that, say for 800 by 600, it'd be like 399 for the line, right? If it's zero based, you would multiply 399 by this bytes per scan line, and that would give you the start, or at least the number of bytes to go into the frame buffer, say to get to that specific, line of pixels in the screen. If you want to use bitmap fonts like I'm going to be using, you take the font height, so mine's 8 by 16, that's 16 lines. We want to multiply that by bytes per scan line. So this times 16 will get the height of one text character that I want to draw with this specific font. And then we can kind of translate that to a cursor position within the screen and do other things with it. So that's what I'm going to be using this value for. But the other ones I'm really not going to mess with. And then in this mandatory info, for VVE 1.2 and above, the X resolution, Y resolution, XY character size, number of planes, bits per pixel, number of banks, memory model, bank size, number of image pages, and a reserve byte for whatever reason. I'll be using X and Y resolutions to check for our desired video mode X and Y resolutions. So for this, 1920 and 1080, or 1920, 1080, and the bits per pixel, I'll be doing 32, just to make it simpler. 32 bits per pixel, 4 bytes per pixel, and it doesn't tell you, but it'll be ARGB, alpha, red, green, blue, that we'll be using. Otherwise, if you need them, then this also gives you the red, green, and blue mask and field positions, which you can use to mask off the RGB segments of your color memory model here for pixels. So after all these bytes, we have mandatory info for 2.0 above. We have the physical base pointer, which this is the physical address for the flat memory frame buffer. So this is where the screen is located. It is returned as an address within this, the physical base pointer. Reserve 2, reserve 3. Okay, and then the 3.0 info and above, we have the linear bytes per scan line, which I think you can use this as well as the regular bytes per scan line. I think they should be the same. Maybe they're different though. I don't know. But anyway, this is specifically for linear frame buffer modes, which is what we'll be using. So linear bytes per scan line, bank number of image pages, linear number of image pages. I'm not dealing with image pages. And then red, green, and blue, and reserved, mask size and field positions, if you need to mask those off. The max pixel clock may be interesting in the future. I'm not sure. This should correspond to the refresh rate for the video mode. So PAL 50 hertz, right? NTSC 60 hertz. But this should correspond to the refresh rate. I'm not sure what it is in QEMU. I guess I could check what it is. I'm assuming it's 30 or 60 or something. And then just a block of reserved data again. So ultimately this is 3 sectors, padding it out to 3. Okay. I also had, so then we had the GDT code. So I might be going back to front with this, but yeah, I'll probably just be copying and pasting. But I'll try to leave enough room for people if they want to type it out. Enough time, rather. So that'd be before the GDT, yeah. Just making it similar to how I had it set up. Okay, so I'll just copy this. All right, print hex, let's go down here. So the way I'm printing a hex string is similar to how I'm already doing in the OS. I just have it here basically for debugging purposes, which I can show that. So yeah, I'll leave this here. Moving to 4 into CX as a counter for how many characters we're going to print out. It's going to be 4 that we're changing within the hex string, which, if you don't remember, is 0x0000. So we're just replacing these with the hex characters we want to print out. And I'm using this hex to ASCII variable or label, this data area here, to hold the ASCII representations of hexadecimal characters. It's a little simpler doing it like that. So moving, I'm assuming the string we want to print is in DX, the hex word. So if it's, 12AB hex, that's going to be in DX when this is called. Moving it to AX, getting the low nibble by ANDing AL with 0F. I'm moving hex to ASCII to BX using xlatb or translate bytes. After this, AL will be equal to BX offset from the data segment plus AL. So if AL is 9, then it'll be hex to ASCII plus an offset of 9, which would be in my string down here, it is the character 9. So if they put in a 9, then this would just return the character 9 in AL. So it's a sort of easy way of doing that. Okay, then the counter, we're doing CX4. So I'm moving that to BX, and then I want to offset into the string and write to it. So AL would be, say, the character 9. We want to write that to our hex string of 0x0000. I'm using that by taking the base of hex string. I'm adding BX as an offset, which at this point will be 4 from CX. So hex string plus 4. And then I'm adding 1 to get hex string plus 5, because that's the end of the string, because we're printing sort of backwards to the front with DX here. Then we're just rotating right to get the next nibble. Rotating right by 4 bits. And then we're going to AND it again, put it into hex string plus BX plus 1, which at this point CX will be 3, and so on and so forth till we're done with DX, which would be 4 nibbles for our 4 hex character string. Okay, then I'm moving hex string into SI, 0E into AH6, because the length of hex string 1 based length is 6. 0 base length, we're offsetting it. But 1 based, it's actually 6. And I'm looping load string byte SI goes into AL, and then printing it to the screen. And then we're looping, which will decrement CX. Then it'll return. Okay. I don't know if I needed to explain all that, but there you go. All right. So let's start copying this other stuff up here. The mode info structure. I'll just copy this first. I guess I'll just copy and explain as I go. Give enough time for people to catch up, hopefully. But the VB info structure function is 4F00 into AX. That's what I'm putting up here. I'm just making AX 0 first and moving that to ES, because ESDI has to point to the VB info block that we want to set up in memory. Otherwise, if you don't set it up in memory, you'll just have to offset from wherever this is returned in ESDI. So it's a lot easier to just label it in memory and then, you know, offset it from labels you have set up. If AX is not equal to 4F, we have an error. So, you know, do an error. Okay. So put this over here next. So to get all the modes that we want to check, if the X and Y and bits per pixel and everything matches up, I'm moving the mode info pointer that we had set up, moving that to AX, moving AX into the offset that we have set up, and then mode pointer plus 2 is the segment. This is returned within a segment offset, setup here, 32 bits. So that's why I'm doing this. Mode info pointer, then plus 2. It's returned within segment : offset. The standard defines it as that. So that's why I'm kind of separating it out. The first 2 bytes will be the offset, the second 2 will be the segment. And the number in the offset moving to SI. Okay. So find mode. I'll just do this short part first. Okay. Our find mode label here, which is probably what we're going to jump to, because we want to do that well, we won't do that. Get rid of that, because we're going to run this code now. Okay, I'll probably put a little thing here. We'll do get next VBE video mode. All right. So I'm moving the segment and offset where the video mode list is contained. Just moving the first mode contained there, which is 16 bits at that segment offset, moving that into DX. I'm incrementing SI twice to add 2 bytes to SI to go to the next mode within the list. That's why I'm doing that. So after we check this, if we need to check the next mode, it's going to be set up. All right. So then I'm moving that into offset up here that we set up. And DX, it contains the mode number from the list of mode numbers, so I'm moving that into our mode sort of data area, our variable. Okay. And according to the standard, the mode list ends with 4 Fs. So if we reach that point, DX will contain 4 Fs. If so, we reach the end. So I have an end of modes thing here. Okay, if not, then we have a new mode to check. So I'm doing the 4F01 function to get the mode info for the current mode we want to check. Move that number into CX. Move the mode info block we have set up in memory down here. Move that into DI. Okay, move that into DI, and we'd use int10h to call the thing. If we didn't get a 4F, we had an error. So that's all that's doing. So with the current mode info that we have set up, I'll keep this code here to print it out, I guess. Just keep that. I'll copy one section at a time. So I'll keep this here because I'll show it for debugging. But we can compare against these, but we can also print them out. So I'm just taking the X, Y, and bits per pixel areas out of the mode info block that we loaded with this function. And I'm just printing them to the screen using our print hex function. If it's 800 by 600, it'd be whatever 800 is in hex, and then I'm going to print a space. Whatever 600 is in hex, then a space. And 32, which is 20 in hex, and then a new line to get the next mode if we need to go to another mode. How do we know if we want to go to a new mode or not? Well, we compare the values that we got. Our width variable we set up, so right now it'll be 1920. If that matches the X resolution for the current mode that we're checking, then we're good to go. Then we check the heights. If it's 1080, we're good to go. Bits per pixel, if it's 32, we're good to go. If none of those are good to go, then we'll go to the next mode. Okay, which code I don't have at the moment, but I'll have in a second. I'll just put this here. I'll move this over. I'll move this over here. Okay, so I'm gonna have these on right now, but I just included this for debugging. These will print, you know, these values up here will be printed to the screen. So this will stop after you've reached the desired mode, because these will all be equal to the ones we're looking for. It'll just stop and we'll see if the values printed are, you know, correct. Assuming the one that we have is the correct mode, our X and Y resolution, our bits per pixel are correct, we want to actually use that video mode. So how do we do that? We use the VBE function for F02 to set the mode with the mode number in BX. We want to enable the linear frame buffer, which is bit 14, so 4000 in hex. So this is what I wanted to show you. 4000 in hex is bits 14. So that's what this is. That's why I'm orienting it with 4000 in hex to set the linear frame buffer, which is bit 14, in the mode number. DI, you don't really need to XOR, but I'm doing it, so. And then call the function with 10H, compare if you got the right return value of 4F and AX. If not, we had an error. And then if everything's good to go, we'll go and load the global descriptor table at this point. If we wanted a new mode, the XY resolution, the bits per pixel wasn't the one we were looking for, we're gonna go to the next mode, which what I'm doing there is moving the segment into FS again. I'm not sure if I need to do this, but I am. So I'll leave it there, I guess. Move that into FS, move the offset into SI, and then we're going to find mode, which is moving that next mode value into DX, because we changed SI here. So since we changed it here, this will be a new mode value when we reload it down there. Okay. So it's not really the best code, but you know, it kind of works, right? Kind of works. And then also for debugging, I had these, I had these small sections set up. It's just, if we get an error and we go to error, I'm just printing an F to the screen to pay respects. And then if we reach the end of video modes, I'm printing an N to the screen to say end. And I think that's all I had in the second stage. Yeah, okay. So hopefully that works to find 1920 by 1080, 32 bits per pixel. If it does, this will halt and we'll have those values in hex printed to the screen. So let's find out. It assembled, which is good. And here we go. So let's check these values here. Hex. I really should make a thing to print out decimal values. It's just slightly more involved and I'm lazy. So hex is 1920, 780, 438 in hex is 1080 and 20 in hex is 32, but put that there. So 1920 by 1080, 32 bits per pixel. We're good. We have found the right video mode. We are Gucci as far as that's concerned. Okay. So I'm going to comment these out again. Alright, now it will load the video mode, but I'm going to halt in the kernel before, because nothing's going to be printed right now because we don't have a text mode that works anymore. We're using an actual graphics mode printing pixels. So nothing's really going to work, so I'm just going to halt right here. So we're just going to have a big black box. Oh, make and make. Yeah, that's why. You can actually run the thing. There we go. So this is, I have a 1440p screen, 2560 by 1440. So 1920 by 1080 does not take up my whole screen, but that's the most common, I think, monitor resolution. So yours, it might be full screen if you're in the same environment I am. But anyway, this is 1920 by 1080. It's 32 bits per pixel. Since it changed to it, we know that it's correct. Again, nothing's printed. We don't have a text mode yet. We have to figure that out. But, you know, that's just good for verifying stuff. Okay. So how do we actually print crap out? Well, that's a good question. This stuff will work by default. Let's put stuff here. Printing a bitmap font. I'm just putting this here because I'm not going to do all this tonight. So I want to know where I'm currently at in this video. So I'm right here currently. So reset screen state. It's clear screen text mode. I'll do that right quick, I think. But yeah, we won't be able to print anything out because we don't have a bitmap font set up. I'll do that in the next part. But let's get at least the screen cleared first. So clear screen. This won't be text mode anymore. So I'll get rid of that. I'll probably change the label as well, but that would mean changing it everywhere else. So let's put another to do here, I guess. I'll put just clear screen because we're not using a text mode anymore. Okay, so instead of B8000, we're not using that anymore. Okay, yeah, so to make it easier, sorry, I keep going back and forth, but to make it easier to work with the mode info block, to get the X and Y resolution and the bits per pixel, yeah, I'm gonna set up, before I jump to the kernel, let's store some stuff in memory. So set up VBE mode info block in memory to be easier to work with. So I'm gonna use 5000 in hex. I'll put memory location. We'll just do that. So let's move, yeah, let's move it to ESI. So what did I call it? It's mode info block. So yank that word. Just paste it there, get rid of that. So mode info block into ESI, into EDI, move 5000. And the mode info block is 256 bytes in length. So divided by 4 for double words is going to be 64. I'm going to move that into ECX. Okay, and then we can repeat and move string double words. So that will move 32 bits from SI to DI, the data at SI to the data at DI. So the mode info block will move into 5000H. 64 double words, which is 256 bytes. Okay, that's all that's doing. All right, then we can use it within clear screen text mode and other places that we want to mess with it. Instead of B8000, I'll probably change these for magic numbers later too. I'll just forget to do it right now. But we can move where that is offset into 5000H that we just set up. So the physical base pointer is what it's called. I call it the frame buffer because that's what I'm used to in other applications. So I'm calling it the frame buffer for me. You can call it the same thing. It might make more sense to people. But frame buffer location and VBE mode info block. So it's 40 bytes into the mode info block. Mode info block is at 5000 plus 40 bytes, 28 in hex. That's where it's at. And it's a double word value. So I'll move it into EDI. The number of bytes we want to write for all the pixels in the screen is going to be 1920 by 1080. That I can't type. 1080 times 4. Because each pixel is 32 bits now. 32 bits per pixel. The color that's going to be in there is ARGB. Should be ARGB, which is alpha, red, green, blue. So this is 8 bits, 8 bits, 8 bits, 8 bits, 32 bits, or 4 bytes. So what do we want to store into the screen? Our color values here. So let's move into the EAX. Let's move a 32-bit value. So ARGB, alpha we're not going to worry about. We're just going to put 0. R I'm going to do 0. Green I'm going to do 0. But we do want it to be blue because that's what we've been using. So FF, I'll just make it the brightest blue you ever did see. So ARGB, I'll do color value, I'll call it pixel color value. Okay. So since it's 8 bits per color, 8 bits for blue here, just set it all ones, it'll be pure blue. So I'll do blue. Okay. So instead of those, and we're going to repeat string double word. Now, we would also normally use the bytes per scan line, but I'm assuming they're going to be okay. So for simplicity's sake, I'm going to hope this works and we don't have to worry about that value. If it did, then we would have to write line by line instead of just doing this in one fell swoop, as it were. And the cursor is not going to work because we're not in text mode, so I'm not going to worry about that right now. Change to not halt here. Okay, simple enough, but I might overlook this, so I'll just put that there. Okay, but hopefully this writes blue to the screen. Let's see what happens. If it even assembles, which it does. Okay, so there we go. It is a little, ooh. Okay, I didn't like that. Why did it go to a smaller number? Okay. Interesting. So it keeps going and then changes to something. It does write blue though. Am I doing something wrong here? Probably. Actually, we don't need to do ×4. Yeah. We don't need to do ×4. This is just number of pixels we want to write. That's what it is probably. It goes and writes it once and then says, what are you doing? And just freaks out. It's number of pixels to write or to draw to screen. I don't know. Writing or drawing, which makes more conceptual sense. I'll just do write. So we want to write this many pixels. Each pixel itself is 4 bytes long, but the number of pixels is just our X and Y values, right? Or X and Y resolution values, rather. So what we could do is also read the X and Y resolution, so we didn't hard code 1080p. That would be something better. That might be for the future. But yeah, the number of pixels we want to write is the size of the screen and X and Y resolution. Each pixel itself will be this 32-bit value. We want to write that many 32-bit pixels. Yeah. Don't put the extra 4. We don't need that big of a number. We just want to write it once. Okay, so there we go. We got our full blue screen. So I just wanted to show, if I can get my cursor back, just wanted to show that's how you clear the screen. Okay, so far when we run the OS, we get nothing but a big 1920 by 1080, 32 bits per pixel square of blue. So we don't have anything printing, and that's where we want to be, at least for this video. We just want to get back to printing text like normal, right? Well, if we want to print text out, we need to have a text to print. There are BIOS function calls I think you can use to get the VGA font that's in video memory, like when we boot up, whatever font's already there for text mode that's built into the graphics card or the BIOS or whatever. We can get that font. I didn't do that. I chose to go with a bitmap font, so that's what I'm going to be doing here. I believe I put that in the source folder. It's not here right now, of course, but I had it in my test, so I'll get that. And test font, this one. So I want to copy that to this folder. So it's there. Okay. So test font.asm. I'm using this as a font file in the file table, and in the future, right now I'm just going to say these files are not technically ASCII bytes. They're not technically binary bytes. They're used as fonts to print, so I'm going to have them as a .fnt for font. That's going to be the extension in our OS. .fnt for a font file. This one I'm just doing 0 to 127 and the ASCII, all the 7-bit ASCII values. This is 8 by 16, although if this is way too small shortly, then I can redesign it to be larger. Basically, 1 byte is 8 bits, and then it's 16 bytes in length for each one, and it helps if you print it out like top to bottom like this. You can actually see the character a lot easier and work with it better. So 16 bytes per character, 127 times 16 for all of these characters are 2048 or 4 512 byte sectors. So at the bottom, I have times 2048 minus $, to find byte 0 to pad it out. ASCII code, extended ASCII table. So 0 to 31 are the control characters, if for some reason didn't already know that, but these are not visible characters. Now, the ones that we do care about are the line feed and the carriage return, but I am already handling those specifically within our print character and print string functions. You know, if we get a 0A or we get a 0D, I'm handling those in there already, so I don't have to worry about it in the font, and they're not visible anyway. I guess it would be better to put them in the font, but they're going to be zeros, so it doesn't matter. We are going to worry about 32 to 127, even though for the space, for decimal 32 or hex 20, it's going to be all zeros in the font. But the other ones, you know, however this is written like a W, the lines for the W are going to be 1s, and the lines for the background, or well, not the text, are going to be zeros. But we're going to go all the way up to tilde and delete, although delete isn't visible either, so there's not really too much of a point in putting it in the font. But, you know, all the visible characters are going to be there. You can see that here. The first 31 are control characters. We don't worry about them. Starts at 32, which is where this is, and that's the space. Starts at ASCII 32 or 20 in hex. So this is just 16 bytes of zeros. The B on the end means binary, of course. And then 33 is the exclamation mark. And if you look closely, you can see the 1s for the exclamation mark. So for these, for the 8 by 16 font, I followed, I think, GNU Unifont is what I took basically kind of copied a bunch of stuff from. But they're not really, they don't take up a full 16 bytes in height. It's more, they start at byte 4 and they end at bytes like 11. I think these are like 15 high. If you go 0 to 15, 14, 13, 12. Okay, so it starts at byte 3 and goes to byte 12 if we're going 0-based indexing there. But you leave some space on the top and bottom for other characters to kind of fill it out. Like the vertical bar kind of takes up the whole space. The curly braces take up about the whole space. The other ones fit sort of in the middle like this. So I go down to like capital A. It'll start here at the top of the A is, you know, at the 4th byte, and it goes down to the 12th one here. So that's what I'm doing for capital characters. For lowercase characters, I think I generally went with 5 bytes of space, and then the character, and then 3 bytes. So lowercase characters are kind of 2 pixels less in height than the full capital characters and symbols. But I have all of them here. I'm not really going to go over all of them. If you want to see them, you want to type them out, you want an example, then I'll have a link to the source code for this OS at the end of this episode, including the font and everything. I'll put a link to that in the description. But these are just, you know, all the characters from basically 32 to 127. It has all the capitals. It has the numbers, you know, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's kind of hard to see, but if you like scroll, since my scrolling isn't super fast, you can kind of see it easier. Kind of like an optical illusion. It's easier to see them. But yeah, those are the numbers. We have, you know, the special characters and symbols, capital letters. At the end, instead of doing delete for 127, I'm making this the cursor character. Although I didn't really need to label this. I could just hard code in the code to just write like a line. But I just put it here for, I guess, in case I don't want to do that. If I want it stored with everything else, maybe the user wants to change the cursor character, I'll have it set up here. So instead of delete for ASCII 127, this is the cursor, which is just a line, kind of like a deep underline at the bottom. None of the other characters go down to the last byte. By using that line at the last byte, the last pixel for line 16, then it appears under any of the other characters, so it kind of works as a cursor, easier that way. So hopefully that makes sense. To have it accessible, we kind of need to load it in. So I'm going to put that in the boot sector. I'm going to load the font. I'll do that last. So I'm going to copy the kernel code again. Instead of this one going to second stage, we'll go to load the font instead. So load font last, or because we need something to print out. Load font into memory 4th. So the font's going to be 4 sectors in length ultimately. 4 minus 1 is 3, which is what we're going to be doing for this. Because we don't want to change our code too much. I'm also going to put it into probably memory location 6000, I think is what I use in my test. So yeah, I'll go 6000. Eventually I'll make a little program to print to the screen where everything is in memory. That's set up, and then I'll make like a memory manager. I have that on the roadmap, just I'm not doing it today. But I'll load this to 6000. So it's going to be, we do need to edit the file table. I can put it last or third or something. I don't really know where I want to put it in regards to the other things. We kind of want it to be set. So I might use it before the kernel and just mess everything up again. That might be what we do. So I will do that. I called it test font. I guess I'll keep calling it test font so that I know it's just a test. It's going to be an FNT style file. It's going to start at 5. Yes, it's going to take up 4 sectors, and it will be just, you know, static on the disk. So we're going to put it and include it here. 2048 divided by 4 is 5. So yeah, 2 plus 3 is 5, plus 4, that's going to be 9. So this will be 9 plus 14, which is going to be 23. 16 plus 7, so that'll be 17. 1 is 18. Everything plus 4, right? So 23, so that's 24 plus 5 is 29, which is 16 plus 13. So that should be D, I believe. Okay. So we want to read 4 sectors. We want to start at 5. Yes. Okay. Instead of loading second stage, we'll call it load font. So that'll be, this will be load font, jump equal, otherwise it'll go to kernel loop. Okay, and this will be, I'll call it like font loop, just to be consistent with, sort of consistent with this naming here. We'll call that font loop. We got the delay. This will go to load second stage. That'll be okay. This will go to load font loop, not kernel loop. Okay, and the rest should work all right. So that'll load 4 sectors of the font to memory location 6000 in hex. Okay. So the kernel will be, everything else will be in different places. The kernel will be E sectors at starting at sector 9. And the file table will be at 17. Still be 1 sector, yep. Okay. We're not changing the second stage. That was kind of the point of putting it right there. First thing that we're loading. Still going to be 3 sectors at sector 2. Okay, that should be all we need to change in the bootloader. So again, nothing's going to happen here. No target to make, yeah, because I'm not in the build folder. But just want to make sure it did assemble. It does not print blue anymore, so we messed up somewhere along the way. So we're, oh yeah, because we have the font and everything. We need to change the makefile. We have a font now, you know. And the font is going to come after the second stage here, right? Yeah, in between second stage and the kernel. So let's put that in. Then this will be test font. Still concatenating everything here. This is going to get real wily real soon, so I need to look in a different way of doing this. Maybe I can pass in an ordered file or something. Like if I can put all these as like lines in a file and then pass the file to cat, and then it'll read it in order maybe. But yeah, let's see if that works now. There we go, now it's blue. So yeah, you got to put the data in there if you want to use it. Okay, but we're not printing anything yet. We do want to print something, so the things we need to change for printing are going to primarily be the print character text mode file, the print string text mode file, and the move cursor file. I don't think we need to change anything else, but if something comes up, then, you know, I'll change it then as well. But we do need to change those 3 things primarily. Where am I halting? I don't remember where I'm halting. Oh yeah, we haven't even got to move cursor yet. I probably don't even need to move the cursor anymore, actually. In text mode, we did need to move the cursor after writing characters so that the next character would print at the correct position on the screen. Here, since we don't technically need a cursor, and we don't have one yet, actually, you can print characters wherever you want on the screen since we're just writing pixels. So there's not really a set area that says, hey, you need to draw text here. This is where it's going to draw. It's wherever you set it yourself, because text isn't really a different type. It's more just a different arrangement of pixels on the screen. We don't really need to do move cursor inside of clear screen. And really, we only need to move the cursor after we're finished writing or drawing something. We don't need to move the cursor after every character anymore, which kind of, you know, wastes some resources. We can just do it after we've written a whole string, for example. So that might simplify some things, actually. I might be able to clean up some code from that. But what I mean to say is, let's, I do want to rename clear screen. I'll do that right now. I'll rename it. Let's rename clear screen text mode to clear screen, which will force me to change it everywhere it occurs. So that's okay. Because we aren't in text mode anymore. So I'll rename all these things that have text mode. Since they will not be text mode anymore. So that'll force me to, you know, be very bad. Reset screen state. Maybe I'll just call it clear the screen, even though it's self-explanatory. I don't know. I'll put that there. Okay, let's go to clear screen, which is not going to be text mode anymore. I'm going to rename it in a second, so I'll get rid of that to do. Change move cursor. We do need to change that, but we don't really need to move the cursor after this stuff, so I'm just going to get rid of that. Yeah. Okay, so that'll simplify that a bit. I'm going to halt here to ensure stuff still works, right? But I am going to move clear screen text mode to include screen, just clear screen. .inc. We'll just do that. So now when we do make, stuff's gonna fail, so we know where we have that referenced. So it was an editor. So clear screen text mode. Let's just get rid of everywhere we have this, which is going to be in a few places, in a bunch of places. Probably could have done this later, but that is all right. We'll just do it now. Have some boring refactoring. You need that in every episode, you know. You need some boring refactoring. It keeps you sane. Although we did rename character and string. So what I need is like an IDE that handles mass renaming, because I don't have anything set up in Vim for that. That's why this is painful. It's one reason why it's painful. Calculator, yes, clear screen text mode is not what it's called anymore. We don't have a text mode anymore. String and print character. I will rename those as well. I call in clear screen anywhere? Nope, okay. And then the file aren't found for the other one. The file is not found, rather, for, yeah, print character and the others. Okay. So include print character. We're going to move that to include print. Just print character.inc. Not print character text mode, just print character. And we'll do the same thing for print string. Print string text mode. We're just going to call print string because there is no text mode anymore. Okay, clear screen already defined. Nice. Now that's good. It's not good at all, but that's okay. I mean, I guess it is already defined in the kernel, but it's whatever. Is it already defined in the kernel? It is, isn't it? Yeah, I called it clear screen. That would be why. I'll call it kernel clear screen, that's fine. If I even need to do that, it's just if we do CLS. I have it as an actual command as well. That's the only issue there. Okay. Apparently nothing else is broken. I don't trust that, but I guess it works right now for the kernel, so that's good enough. Okay. So yeah, I do want to get to where this prints out. So print string text mode, I do need to change that. So I need it to be print string, not print string text mode. That's gonna be a fun change. Print string text mode enter. There we go. Let's change that to just print string and not do that. There we go. Change that to print string. Okay. Let's do dot dot. And that's all that she wrote. Cool. I did change it in there. Okay. So print string.inc, this is going to rename to print string from print string text mode, rename that. Okay. So can I actually get to what I wanted to be doing? Yes, yes I can. I will get to that. There we go. Super long file, but there we go. So this is the version that I did that works with, you know, printing the bitmap font. So that's what I'm going to be kind of explaining, copy and pasting again. So EDI with the row to column to print to. We're not going to print with B8000 anymore. Not anymore. Again, we're going to move the frame buffer that we're using now, the linear frame buffer address at 5028 that we loaded in the second stage bootloader. So we'll do that to EDI. Move the bytes per scan line to AX. I XORed just so the upper 16 bits weren't there. This is a bad way of doing that. That's a bad way of doing that, but you know, it works. It's just extra. Let's just copy all this. Might as well. Copy it before the loop. Okay. Get rid of this stuff down here. That was the old stuff. Okay. What exactly did I change for this so far? I'll put spaces here again. So we're still getting, this is the same, getting the Y address, but now I'm getting the value at that address. And I realize the value is just a word and I'm getting a double word. That's not really good, but you know, that's what I'm doing here. That's why I'm doing this. So actually I probably could just put that into BX. Yeah, blank out the upper 16 bits because we're going to be using EBX for, I'm shifting left by 4 to do a sort of hopefully faster multiply by 16 because 2 to the 4 is 16. So shift left by 4 effectively multiplies by 16, which is the height of our character in our font, which is 8 by 16. So I'm basically translating the Y cursor value into the right area on the screen where the character is supposed to go, is what this is doing. So multiply by 16 the Y value. So I'm multiplying by the bytes per line that we put into EAX. So I'm getting the right line on the screen that we're supposed to go to by multiplying by 16. So if we're typing in character row 3 of text on the screen, that would be 3 times 16. But we want to get the byte value of that row so we can write to the right byte values inside of our frame buffer, inside of video memory. So I'm multiplying by the bytes per scan line here to translate that row to the actual byte value on screen. So I know this is kind of confusing, but that's what this is doing. So the row to print to in bytes, effectively, I'm ultimately putting into ESI here. Then I'm doing something similar for the cursor X that we did for cursor Y. So I'm getting the address, getting the value. Again, I think I can just move that into BX because it'll be a word value. Blank out the upper 16 bits by ANDing with 4 zeros on the top. Shifting left by 5 because our font is 8 by 16. The 8 is the width of a character. That is 8 pixels. And since we're working with 32 bits per pixel, 8 pixels is going to have 32 bits for each one of those. So 4 bytes. So 8 pixels times 4 bytes is 32 bytes. That is the width of one character effectively in the frame buffer. It's going to be 32-bit width, 32-byte width per character. So shift left by 5 is 2 to the 5 or multiplying by 32. We're getting the Y value in bytes and we're going to add the X value in bytes, right? That's how we get the right byte location in the frame buffer to print to. So after that happens, I'm going to add the X value in bytes to the Y value in bytes that we already got here, or the row in the column. And I'm going to add that, since we moved the frame buffer location into EDI, I'm going to move that row column byte value offset from the frame buffer by adding it to EDI. So we add it to the frame buffer to offset into it to get the right location to print. Okay, so after all that big mouthful is said, the character is still going to be an EBP plus 16. Yeah, the address of the string. We're moving to ESI like normal. Okay, I guess I'll put a little space there. Okay, so the loop that we're going to use to print is going to be a little bit different. A fair tad bit different, maybe. That I did XOR EAX first, just to ensure that the upper, well, in this case 24 bits, is going to be cleared out before we do load string byte to get the character we want to print from SI into AL. But these comparisons are the same. Store string word we're not going to do anymore because that's not how we're printing. We're not in text mode anymore, so I'm going to get rid of that. I'll copy what we have over here and try to explain it as worst I can. Increment cursor, X address update. What all am I going to do? I guess down to LF. 52 lines yanked. Okay. All right. Let me just get rid of this stuff that we had before. What stuff did we have before? We had this. Yeah. Okay. So when we actually print the character, since it's a bitmap font, we kind of map to the bits that we want to print, the font, where that's stored. So we want to load the font where it's stored in memory, which is at 6000. I'm going to put that into EAX, but we're going to offset into 6000 the character that we want to print. So this is nice because ASCII, it's all linear, it's 0 to 127 or whatever. So if we have like a capital A, the ASCII value of that capital A that's going to be assembled by the assembler is 65, I think. So the 65 there is going to be offset into our font to get the right start of capital A in the bytes that we have that we're going to use. So we're shifting left by 4. Again, each character is 16 bytes in length. So from capital A to capital B in our font file, that's 16 bytes. So we multiply by 16 bytes the character that we have. And then to get to the start of that character, I'm subtracting 16. So I could probably do this better than a shift left 4 and a sub 16, but that's what I'm doing now. If we multiply by 16, we're going to the end of the character. We want to start printing from the start of the character, print top to bottom in pixel order. So that's why I'm subtracting 16 here. And then we're offsetting into where the file is located in memory at 6,000. So we add 6,000 to that. And then I'm pushing a D word here just to save the height of the character, because we're going to pop that out down here before we draw the next line. So that's why I'm doing that. The number of bits that we're using, we have an 8x16 font. The number of bits for each line, number of pixels per line in their character is 8. So I'm moving 8 to ECX for a counter. So to start off, I'm getting the bytes of the character that we have in AX. So if it's capital A, we're getting the first byte of that capital A. The first 3 bytes, if you remember, are going to be 0 before we actually start printing the pixels for the text out. But, you know, we got to read top to bottom regardless, so we'll just do this. We get the byte of the character that we're currently on. I'm moving it into BL just for an area to have. And then to set up for the next byte, I increment EAX first. So the actual bit loop here, to store the counter, I'm just using another register using EDX here. So this is the bit counter. So we start on bit 8. I'm decrementing EDX because I'm going to use bit test. And bit test assumes a 0-based indexing for bits. So the least significant bit is going to be 0. The most significant in this case is going to be 7. So I'm starting at 7. Test font, yeah. So if we have something like the capital A, we want to read this left to right and top to bottom to actually print the character out as it's stored here, as it looks here visually. We want to read left to right and top to bottom. So I'm starting at bit 7, 0-based, 7, 6, 5, 4, 3, 2, 1, 0. And I'm going to read bit 7, then bit 6, then bit 5, 4, 3, 2, 1, 0, go to the next line, bit 7, 6, 5, 4, 3, 2, 1, 0, next line, so on and so forth. If we read a 0, I'm going to print out whatever background color we're using for our, I don't know, whatever we want to draw at. Right now it's hard-coded, so I have it as blue since our background has been blue. But if it's a 1, we want to print the actual text color. So if you want to think of this as text foreground and background color, like it was in the VGA color text mode, if that helps, that's kind of what we're doing here. The 0 is going to be the text background color. The 1 is going to be the text foreground color, which right now I'm just doing white. I might make it a little less contrasty in case it's blinding white. So what I can do instead is make all these E's for a slightly grayer white or something. It'll be gray. So the first bit's going to be 7 because ECX will be 8, moved into EDX, decrement to 7, bit test BX, because bit test needs at least a 16-bit register to work. But you can reference the other register here, DX, which will be 7. So is bit 7 set? So if we get the first byte, this is bit 7, it is not set. So the carry that the bit is copied to, the carry will not be set, so it'll go right here. And it will move the text background color into the 32-bit double word text background color blue. It'll move into EDI, which at this point is referencing the byte space on the screen that we're going to print the character to, since we converted the cursor into the character byte address sort of in the frame buffer. So that'll be correct. Now if the bit was set, like when we get back down to this row in the A, then we're going to print, you know, our text foreground color. I'm going to jump down here, do this. But regardless, after we move the data for the background or foreground color pixel, we're going to go to the next bit by incrementing by 4 bytes, EDI, because each pixel is 32 bits. So to get to the next pixel, we need to add 4 bytes. And then I'm going to decrement ECX right here, to get the next bit. And we'll move it into here. So ECX will start at 8, it'll go to 7, and then this will be 6, and then we'll do this stuff. So I probably don't need to do this, actually. I could just have ECX be 7, and then bit test with CX. So that would be a simple improvement. I'm not doing that right now because I want to ensure this works first. But that's something to keep in mind. Low-hanging fruit there. But that'll go through all the bits 7 to 0. When all the bits are up, ECX will be 0, and it will go on down here. I'll pop what we pushed up here, which is initially 16 for the height of the character. I'll pop that into ECX, decrement it, so it'll go to 15, meaning we have more lines to print in the character. So if we have more lines to print, we're going to keep going on. If we don't have any more lines to print, we're going to go and increment the cursor because we printed out our full character. But if we have another line in the character to print, then I'm going to zero out EDX, move bytes per scan line to EDX, and go down one line on the screen. So I'm basically, I'm just adding the bytes for a full line of pixels to EDI to go down one row of pixels in the screen. So one row of characters would be times 16, of course, for the height of the character, but this is just one row of pixels for the next sort of line in the character that we're going to draw. And then I'm going to subtract 32 because the width of a character is 8 pixels or 32 bytes. So after we print out one line of the character, we're going to be 32 bytes over to the right. So we want to subtract 32 to line it up for the next line. Otherwise, we'll have like a staircase effect. It'll be this line, then this line will be to the left, to the right, and then it'll go like diagonal down. We want it all to go left and then go back to the front and then print and back to the front. So if my finger is better explaining. That's what we're going to do there. Okay, so after we printed out our character, we want to get the next one. We're going to increment the cursor because we already printed the character out. Go to the next position. I'm multiplying. I'm getting the character height minus 1 because we will have ended on line 15, I guess, because it's 0 based. And then I'm subtracting 15 lines from EDI. So after we print a character out, we're going to be sort of at the last line on the character, which is sort of 15 or 16 lines from the top of the character, right? Because the height is 16 lines. So we're going to be at the bottom, sort of underneath the character after we finish drawing it. We want to go back to the top for the next character so that they all line up in a row, you know, for proper sentences and words and things. So that's what this is doing. Basically subtracting the height of the character in lines from EDI to go back to print the next one. Okay, then I'm moving the X address back. Doing the same thing we were doing before in text mode, updating the cursor position that we passed because we passed in the cursor XY addresses. I'm still using 80 character length right now. I might change that later, but right now it's still 80 character length, so people should be happy about that, right? So that's the same. The only difference here is, XORing EDX, just to blank out the upper 16 bits. I'm moving the cursor X value. Is that what this is doing? Yeah, I'm moving the value that we just updated into DX, shifting it and multiplying by 32. And I'm subtracting that from EDI. So this is if we have a carriage return. If we don't have a carriage return, we're going to get the next character and go to the loop, right? But if we're at the end, we're at the, we printed character 80, we want to go on, then to do a carriage return, that's what this code is doing. I'm taking the 80 characters that we printed, which is what this should be. I'm multiplying 80 by 32 because each character is going to be 32 bytes. So 80 characters times 32 bytes. And I'm subtracting that from EDI to go from the end of the line in bytes to the beginning of the line. And then after we do that, the cursor position is technically 0 for the new line of text. So I'm setting that to 0. And yeah, the line feed is a little different. What buffer was it? Okay, actually it might not have been. Oh, I changed this value here. This won't be 36 anymore. This will be different, but so this will be different. So we have 1080 pixels. So what is 1080 divided by 16 for our character height? So this is how many rows we should be able to fit in the screen ultimately. Maybe one less. It might look a little jank, but I'll try one less just to see how it works. So I'm going to do 66. So if we're at line, execute order 66. If we're at that line number, then we're about at the bottom of the screen. We want to kind of scroll at that point. We want to have scrolling still. Yeah, 66 times 16 equals almost 1080. It's a bit less. It's actually exactly 16 less. We could try 67 actually. Let's just do that. We'll be risky. If it doesn't scroll, then we know it doesn't work, so that's okay. But this evenly divides, so this should be okay. Okay, this is different. So get rid of that stuff, because we're not doing that anymore. What we are doing is getting the bytes per scan line back into AX, XORing to 0 out the upper 16 bits again, multiplying by 16 to get the character height and lines as a byte value. going down one character row. So I'm adding 16 lines worth of bytes to go down 16 pixel lines within the screen to go to the next line to print text at, right? That's what I'm doing here. And then we're getting the X address that we want to print back in because the loop assumes we have the X address in EBX. That's what this is assuming when we get down here, but anyway. Okay, the CR is different as well. Just did that so that I can know where this stuff ends. Okay. This is the same thing we did up here for the carriage return. It's the same thing. Except we have to have an X address first to get the value. So that's all I'm doing. Okay, scroll down will be a bit different as well. It might be simpler, I don't know. I put a lot of code here, so let's just copy this. Copy and pasting always fun because I don't have to type it out anymore. I didn't have to copy all that though. Let's just do this. The ESI, EDI, that's the same, so we'll do this. Alright, and then I'll get rid of this code we had previously, but I'll leave that. And get rid of that. Okay. That's alright. Alright, so to scroll the screen, I'm gonna have to reset the frame buffer where we're gonna get data from. So just resetting EDI to the frame buffer address, moving that to ESI as well. So ESI points to the frame buffer. Blanking out the upper 16 bits of EAX by doing that because I'm gonna move into lower 16 bits, the bytes per scan line value. I'm shifting left by 4 to multiply by 16. So we get one character height in bytes, you know, to offset by. So by scrolling, we want to take the number of lines we can fit on the screen minus 1, and we're going to scroll that data, you know, like we were doing before in text mode. We're going to take lines 1 to whatever and put it into lines 0 to whatever minus 1 to effectively scroll up and blink out the last line every time we need to scroll a line of text. That's what this is doing. So one character line is going to be the offset. That's what I'm getting here. And I'm adding that to ESI to make it sort of character line 1 in the screen in bytes. Okay. So this, I had written out the math for 800 by 600. I need to change this because this is all hard coded, which is bad, but oh well. This is going to be 1080 lines, not 600. So 1080 lines minus the 16 line character height is going to be 1064. So 1064 times the bytes per scan line, which is going to be 1920 times 4 bytes per pixel. That is going to be, let's see, 1920 times 4, 7680. 7680. Okay, so 1064 times 7680 is going to equal whatever these things are. So 1064 times 7680. This is a lot of bytes that we're moving. If you couldn't tell, there's a lot that goes into each frame in your like super awesome game like Call of Duty, Modern Warfare, or whatever you have. There's a lot of bytes that are being pushed around very fast. So 8171520, 8171520, or hex 7CB000, 7CB000H. Okay. Now this does fit within, it's 4, 8, 12, 16, 20, 24. So it fits within 132 byte value, so or 32 bit value. So we can still put this number into a register to work with. So that's good. That's the number of bytes that we're going to be moving here. And we'll divide it. So 8171520. I guess, divided by 4, so that's how many double words we want to move. So 520, so divide that by 4, 2042880, 2042, or 1F2C00, 1F2C00H. That's how many double words we're going to use. So that number is a lot smaller than the other number, right? So that one's not as hard to work with. That's the number of double words that we're going to move just to make moving data around a little easier for the CPU. And that will scroll the screen up by 1 line. So that's what that's doing ultimately. For 1920 by 1080, you know. But we can also get the values from the mode info block that we saved at location 5000 instead of hard coding things, which might be better for the future, but that's what I'm doing right now. At this point, EDI points to the last character. So 800 pixels would be 1920 pixel per line times 16 lines. Do decimal here. 1920 by 16 is 30,720. 3720 times 4 bytes, which we're going to divide by 4 anyway, but anyway. Times 4, 122880. 122880, just to give you, that's how many bytes that we're writing in the last line alone, just for all the characters. Potentially, although we're only moving 80 characters, so we don't need to do the whole line, but this is a little inefficient, obviously. But that divided by 4 is going to be our original number, so 3720. In hex is 7800, so I'm just going to put 7800 double words. 3720 or 7800 double words. Okay. So what am I doing with that? We're going to put it in there. That's how many double words we're going to move the pixels into for the last line. It'll need to be the text background color, which is blue, so it'll look better and not weird. And then this rest is the same, so yeah, hopefully a lot of that made sense. I don't know. This will be last line minus 1. Ultimately, that's what we're going to print at. Or well, it should be the last line actually. It should just be the last line. An X address we're moving back for the loop. That should be all we need to change for print string. We will have to make similar changes for print character, but I want to make sure print string works first, at least for this simple example in the kernel, before we go changing everything else. So this will break everything that we called print string text mode, which is showing up here. So I'll go ahead and change those as well. Eventually we'll get to the payoff of seeing this work, I promise. It'll just take a while. It'll just take a while. Print string text mode. That is in calculator. Yes, it is. Call print string text mode will now be called print string. That's the only area we have it. And in the editor, of course. Yeah, okay. So we'll do that. Yeah, I'll just replace it with print string so that we can do find replace faster. That was the last place we had it. That's not too bad. So print registers also references this. And I'll do the star so I have it saved. And again, we'll do this. Print string. Well, don't do that. There we go. So this appears everywhere in a half, but that's all right. Just find and replace print string text mode with print string. That's all I'm doing there. Okay, undefined symbol. So that is in print file table as well. Yep. That is true. Find replace it. That's the only time we have it. Okay, good to know. There we go. Okay. So I'm gonna check if the OS boot message prints. That's all we've gone and done. Just change printing and everything just to make sure that the boot message prints, right? But it doesn't take that long to fix everything else. I just want to make sure that prints. All right, and it does. Look at that. It is kind of, the way I did the font, it kind of, you know, hugs the left side. So I might want to change the spacing on some of these characters, or well, all the characters do not start immediately on the left. It depends. I don't want them to touch on the right either though. So I might have to mess with it a bit. We have our custom font printing. This is 8x16 mode in a 1920 by 1080 video mode. So 8x16 characters rather. Hopefully this shows up okay on the video. I mean, on my screen I can see it, but on your screen maybe it's small. I can blow it up a little bit, but if this is too small, let me know. I can make a larger font, but this is what I'm going to be going with for now, barring any people tell me it looks like crap, so which it might look like crap, and it's kind of small to see, but that's, you know, the OS boot message prints, so that's good. That's good to know. I'm going to change print character as well, and then we'll go from there and see what else we need to fix and debug, and yeah. Okay, let's continue on and change the print character text mode, previously print character text mode file, and make it sort of equal to the print string file that we now did, so that all the printing changes are fixed everywhere, or well, changed everywhere to work with our bitmap font. Let's do that. I don't need to say that many words to say what I'm trying to say, but then again, I do. So again, we're going to change this stuff here. Instead of a loop, it will be different. Start of string to print will be an AL. We'll just go to here. This will be there. Oh, didn't need to save that. Okay, but that's all going to be the same, so you can just copy paste, you know, that stuff there. That's going to be the same. To get the right byte value in the screen, we want to print the character at. So the previous stuff that we had, we can get rid of. I'm going to keep this line here because we do need the character. The colors we're not going to use. I could add the XOR as well, just to make sure those are clear. We'll add the XOR there. Character return to line feed, we're not going to do the store. We won't be doing this in a loop, we'll just be doing the print character stuff really. So we can copy from print character down, sort of, where did we end? Where's the LF? Because that's where I'm kind of eyeballing here. We'll copy down to right before the LF, we'll do that. We will do that. And let's shift this over 1 because it's over a bit too much. Yeah. And the cursor as well. It's all over a bit too much. There we go. The cursor position update. Can get rid of this stuff. Instead of loop, we're going to end print. So I can keep that. Just change that to end print. So what else? What would I need to change for this, if anything? We're doing just the bit loop again. We're only going to print a single character though. Go down one line, move one to back up. We're not going to character loop here. We don't need to push ECX. So we don't need those two final lines there. Cursor will increment and go on. That should be okay. And then we will need similar LF and CR changes, I think. This will be 67 instead. I'll just copy it down here. Get rid of that one. And then this, I'll copy. But yeah, this will be in print. No, don't do that. Shift V and then do that. Okay. Because that'll all be the same. And this will be the same as well. Okay. And then scroll down will be the same. So these files are pretty similar. It's just the print string has a loop, the print character doesn't have a loop. It's just, you know, one at a time. It's just one at a time. And this is easy to see where the other stuff is because that's, the new stuff is indented. So that's, you know, unexpected good thing there. I'll go up this time to be different. Shift it over. Okay. That should be all we have to do. Assuming we didn't mess anything up like loop to imprint. That should be all we have to do. Again, make is gonna fail. It should have failed. Oh, we didn't change this. This needs to change to print character. Now it'll fail. That I can change as well. And the file names are shorter, so that's good. That's saving some bytes here and there. Always good, always good. So now this will fail. Yep. We need to change where it's printed everywhere. Character text mode, I'm going to change to print character. So find replace, there we go. Have to change it in the editor as well. Undo all that. Print character text mode. Change to print character. Find replace all the things. I'm pressing N and period because Vim is cool like that, but I do want to see everywhere I have it, which is a lot of places. That's why I talked about making subroutines for it. There we go. And in the kernel. Don't want to do that. Print character, we'll just leave that. We'll leave that extra line there for any OCD people. They'll enjoy that. Alright. Probably in the editor, actually. Yeah, I have a lot of print character stuff in the editor. Yeah, jump not equal dot print character. Well, that should be okay. It just looks bad. Oh, this, yeah, we have jump print character. Okay. It's a label. So I'm going to call this text edit print character. That's what we're going to call it. So wherever I have jump print character, treating it as a label, I'm going to jump to text edit print character, which I think is what I called it. Yeah, okay. And we don't like it in print file table, that's true. Print character text mode will be print character. We'll change all these. Hopefully it wasn't a label, I don't think it was. And do I have a final file that didn't work? Print registers. Yeah, we do want text. Change it to print character. Only those two places, really? Well, that's useful. There we go, okay. So where are we at in the kernel? We just did this. Okay, so let's see what doesn't work now that we changed those two things. Let's just see overall what is still broken. Now, actually the move cursor will be broken because we don't have anything that we're doing for the cursor. We should still be able to write characters. No, we can't. So never mind. The prompt prints. So we know that the prompt is correct. So prompt for string, yeah, move cursor after prompt, that probably isn't correct. So yeah, we need to change move cursor. Be under screen, move cursor. I'm going to take what I did for my OS tests here. Just set up the same way. So again, I'll probably be copy pasting and trying to explain. So this video isn't 3 hours long again, although it might be, unfortunately, we'll see. But I moved extra registers. Oh, I didn't change that to do. I had that in my test as well. That's good. Parms off the stack is a little different. So just to blink out the upper 16 bits, I'm XORing first. Moving that. And doing this, getting the character width, yeah, in bytes. XORing these two for later. Okay, that's AX, so I'm shifting left, doing this, and this. Calculate cursor bytes. So I'll do that here. So this is what was previously here, and this is the new stuff. So we're doing the same thing for the row, getting the value in character lines, and then multiplying it by the bytes per scan line to get the value in bytes for the screen. Adding the byte value, getting the byte value for the row, because this is the row value, putting that in EAX, and then adding the byte value for the column, which was in EDX. So getting the byte value for the cursor into the screen in EAX. And then I'm offsetting that from the frame buffer location to actually get it correct, and, adding that to EDI for that. Offset it from the frame buffer. So yeah, I did the same sort of bit loop thing, but a little smaller, because we're just drawing the cursor, which is character 127 in our font file, which is just the underline at the bottom of the cursor space, or at the character, the bottom of the character. So I did that instead of the other stuff. So I'm going to put this here, and I'm going to get rid of what we previously had because we don't need that anymore. We're not dealing with the CRT hardware cursor anymore. We're just drawing basically a line of text. Of course, if you wanted to change the cursor, then we can draw the whole cursor out. All 16 lines. I just want an extra line. There we go. But anyway, the cursor is at location 127, or well, yeah, the offset for the character 127 in our font file. So multiplying 127 times 16, which is the height of a character. For this one specifically, since I'm only drawing one line at the bottom, I'm just decrementing 1 byte to only draw that one line. If you have like a full block for your cursor or whatever, then you'll want to, you know, draw the whole thing. But I'm just drawing the last line. That's why I'm decrementing 1 instead of 16. So EBX still contains the bytes per scan line. So we're getting 15 lines to get to the last row because it's 16, but we start on the last one. Yeah, I'm adding 15 to EDI. So EDI will be at the top of the character we want to draw, the top line of the character that we're going to draw, line of pixels. We want to go to the bottom, line 16. So if it's at line 1, we want to add 15 lines. So that's what I'm doing here. 15 lines times bytes per line to move into EDI, to add to EDI, to get to the bottom of the character space that we're writing. And we're doing something similar to print character and print string. The number of bits we're going to check is 8. And the next byte, the 1 byte we're checking really, we're moving into BL from EAX. And I don't need to increment here because we're only doing 1 byte. So I really don't need that actually. But the loop, again, ECX to EDX or bit counter decrement because bit test is 0 based. And if it's a 0 or a 1, we draw the text background, which I'm going to make blue. Text background color blue. Or the foreground color, which is white, but I made it like, I was going to make it sort of grayer color than pure white with all E's there. The next pixel, yes. If it's not 0, we get the next bit. If it is 0, then we've printed the character, so we're good to go. Hey, so that's nice. So that was move cursor. We're just printing a little line for the cursor. So let's see if this works any differently now. Okay, so now if you can see, yeah, I have the little line there corresponding to where our cursor is. So we know we're going to print here. Again, we can print dir. Nothing shows up, which is not good. So we have something wrong there, and that's, I guess, in the kernel. Because what we print is not showing up. So now we enter the debugging phase of the video once again. That's always fun. So I don't see what I have different here. Oh yeah, that's what I have different. Yeah. Since addresses are 32-bit, we need to use ESI, and I guess ECX would probably help as well. Yeah, ESI is where command string is. SI is not guaranteed to be correct for anything for this because addresses are going to be 32-bit. So that's not good. That might fix the key loop. It might not, but it might. It doesn't. We don't get anything. And if we print, we get all this. Okay, I found the issue within our print character file here. So at the bottom of the character loop, I was not looping back to print the next line of bits, the next line of pixels, checking the next line of bits rather. So yeah, I might have gotten rid of this because I wasn't paying attention, probably, because I do that a lot. But anyway, we need to add a push ECX to push our, if we start at 16 lines and we print a line, we decrement to 15, we need to push that to check again on the next go round. See if we're done printing the number of lines for the character. So yeah, push ECX here and then jump back to make the loop again. So I'll put that there. So this whole thing is, a loop. Yeah. Okay, and then under increment cursor, we do not need these 4 lines that we have. I commented those out, but we don't need these because we're only printing 1 character. We don't need to move for the next character. That'll be taken care of whenever we call print character again with the cursor X and Y addresses. So we don't need to do this. You might be able to include it actually, but we don't need it. So there's no use having that there. But those are the only changes we need. So if we make run, stuff prints out now. So dir is directory. If I press enter, hopefully it works. There we go. So we do have extra, move cursor lines here, but printing should work the same as it did before. So let's just, load a file in the editor, load the file table, say, Actually, loading didn't work, so never mind. Because we have to change, yeah, the load and save file to work with the different sectors that stuff are contained at now. So yeah, that stuff is contained at now. But anyway, move cursor. There was some extra stuff on the line there in print file table. So let's look at that right quick first. That'll be a low-hanging fruit we can take. So we don't need to move a cursor to print characters out anymore. We only need to move the cursor, which really just draws where the cursor should be. We only need to call move cursor after we're done printing whatever it is we're printing. So, you know, a lot of words about nothing, right? So we don't really need to move this here after we print the heading, since the cursor addresses and values will be updated accordingly. File name loop. So we print the character to screen. We don't need to do this. We don't, I guess we'll keep the restored values. It's fine. So we want to print blanks. Print character, move cursor. Really, we really don't need to do all this. So if it fails, then I'll add this stuff back. That's okay. But I really don't think we need to do all this. Printing blanks, print character, because move cursor, all it's doing is just drawing a character to the screen, wherever we're currently at. We don't need the underline if we're still printing stuff out, right? Right. This goes after printing the hex values and stuff. Okay, so here we're printing the new line, the carriage return and line feed after the current line and the file table is printed out. Yeah, we don't need all these move cursors. They're gratuitous. I guess we can keep the ending one. Really, we don't need any of these, I don't think. Because when we return, we'll print the prompt in the kernel, and then that will print the cursor after the prompt. So we really shouldn't need any move cursors in this file, I don't think, to be honest with you. We really don't need any of these. And we can see that in effect here. If I'm not talking out my butt, and I'm not. We do have an extra one here, but this is from print hex, I believe. So print hex has extra move cursors we don't need. That's what I'm trying to say. So we can, you know, simplifying stuff is nice. I like that. Yeah, we don't need to do this. Don't need to do that. Okay, so let's make run. So just to get the directory to work, there we go. Now there's no extra extraneous cursor lines. It's only here at the prompt. So loading and saving will not work, and deleting and renaming shouldn't work either. Because, and we get some extra move cursor there, because the sectors aren't right for the file table and stuff in the discops file. Okay, so we need to fix that. The only other thing we would need to fix is, I remember having issues with backspace, so I think we need to fix backspace as well. If I do dir backspace dir, it works, but if I do 2 backspaces and put ir, it doesn't work. Also, when we backspace, we have extra move cursors we don't need. So I did fix that in the test. I'm just doing these right now because, again, they're low-hanging fruit. They're easy to fix, and I remember that this was an issue. So we need to get the backspace code up here. So I am glad that I saved it. But the backspace code that I did, I think, was just printing 2 spaces and then going back. So I move back 1 space, then I'm printing 2 spaces at the cursor instead of 1 space. Actually, let's get rid of that. Print 2 spaces at the cursor, and then move the cursor back 2 spaces. Because it moves it forward, right? So decrement word 2, or well, sub word 2, and then move the cursor 2 spaces. Okay. And that should fix backspace. So if we print dir 3 characters and we press a backspace, it'll move the cursor back. It'll decrement the cursor x value to move to the r, because we're after the r if we print it out dir. So we move back to the r, we print 2 spaces, because the one after the r will have the previous move cursor applied, so it would leave an underscore if we didn't do this for the cursor. So I print 2 spaces to blank out the r, and then the leftover cursor line after the r. And then I move back 2 spaces after we did that. That's, you know, so hopefully that makes conceptual sense. So instead of leaving extra spaces when we do backspace, now it disappears. And it should correctly, well, should correctly, it doesn't, but it should correctly the command we want to do. So I guess I need to change some more stuff, huh? Figure it would be a tokenized input line. Oh, here we go. SI. This needs to be ESI. At the end of the get token loop, that needs to be ESI. Because ESI points to command string and our tokens and stuff because it's, you know, using addresses. Addresses are 32-bit and we need ESI right there. I don't know if that was the issue, but I mean, that was something. That wasn't the complete issue. Okay, I need to find what this is. Oh, I blanked out command string as well, it looks like. So let me copy that over. I don't know if I needed this, but I did do this. Blank out command string before we get the next line of user input. That's what this is doing. Command string 255 bytes long, so I'm just blanking that out. Oh, I do move a byte to 0 as well, it looks like, yeah. So key loop, I'm moving whatever byte we're on when we decrement, moving a 0. So if we typed in dir and we go back, I'm moving a 0 there, so it would be di0. Because I think before in my testing I was leaving an extra character there, so if I did dir backspace backspace ir, when I was testing it would leave dir for some reason. It wasn't getting rid of the extra I, or it was putting in extra I, so I don't know. But that, I think this fixed that in my tests. I'm also XORing EBX down here under next token, because we're pushing EBX on XOR to wipe those bytes out just in case, because we're doing tokens plus BX. We're multiplying BX, so we do need that to be correctly. And then, no, instead of add BX2, I'm doing increment EBX. Because that might be slightly faster. I don't know. Instead of doing add 2, we can do increment twice and make sure it's EBX as well. Okay, I found the issue with the backspace and printing some characters and stuff. It is with move cursor, so in the movecursor.inc file. If you look right here, the modified registers, should be an S there, is EDX, EBX, EDI, and ECX. Now I did not have those at the bottom. These were gone. It was just EBX and EDX. So you need to add in pop EDI and pop ECX above those bad boys so that the counters for everything, ECX is correctly returned, as well as EDI. So if we do that, and you just might find you get what you need. No, yeah, you get what you need. So dir backspace backspace, dir still works. You can even undo the whole thing, type it in again. Hey, that wasn't working before, now it does. That's awesome. So the only other thing I was thinking of was what, with the disk stuff, right? Since this stuff isn't going, yeah, fileops.inc, since that's not going to be correct from the file table, we need to change some stuff there to make sure the commands still work. Rename, delete, and loading and saving files wherever we're doing that. This is the file table is at sector 17 now, and it is one sector. So it did need to change that. It is still at memory address 1000. That is okay, but it is at sector 17. The blank data uses variables for these, so we're okay. Okay, load file should be the same thing. Those are okay, but rename file, again, yep, this needs to be 17. Save file, I think we're changing it as well, right? Yep. 17. But it uses variables in the other places. Okay, then that's okay. So let's see if stuff works now. So dir, can we load from the shell file table? No, that works, yeah. It does have an extra move cursor there we might want to take care of, but that's all right. And load file works in the editor. That's good. That's good. Okay, so let's rename editor to text edit. So extra move cursors on returning from rename as well. Text edit, that's renamed. And it still works. We do have issues with drawing strings as well at the bottom of the screen in editor. I do need to change that. But we can at least save stuff, maybe. It looks like that worked. It's just not showing up right, but it did work, and it did show up there. No, we can't run. Oh, because we called it text edit. Yeah, I'm stupid. I just renamed it. That's why it doesn't work. Okay. So let's delete. Make sure deleting works. It does. So rename, delete, save and load work. We just have to change where move cursor is after returning from some things in the kernel. And we need to change editor to print strings out correctly and everything. Okay. Those should be the last two things. Okay, rename file. When we return, we do not need to move the cursor because it will do that when we do get input. After we print the prompt, we'll print it after. So we're good there. So the other one was delete file, right? Yep. So move cursor we don't need under delete file. Get rid of those lines. Okay. It making more urns. One of these days we'll get a pottery class going, but not today. Let's rename file table to FT. We still get an extra move cursor there. That's from the enter from the command though, not from the rename. But it did rename that. Okay, and we'll delete FT, which is not good. We don't want to do that. Let's delete calculator. Okay, dir, yep, and it's deleted. All right, cool. Actually, let's make sure calculator works. So 190, I guess that's right, 10. So we got some extra move cursors in calculator as well, but I think it works all right. Okay. So let's see where that's going on. Move cursor forward. What if we press an enter key? Print the new line, we don't need that. And we return. When we return, we'll have it out anyway. So that might be what was happening. So we don't need move cursor under the print new line stuff in the calculator. Right? Yeah, there we go. Well, we do need it after, actually. Dang it. We need the last one. Calc cursor Y, calc cursor X, call move cursor, add ESP8. Okay. Just want to make sure it works. Yeah, we have it there, the cursor underline on the next line so that we can input more characters. Oh, I don't have backspace. So 2 times 10, 20. Okay. So let's change the editor. Actually, just writing stuff to screen is wrong. And I know I changed this in the tests that I did. We'll have to change some things definitely, like this. Fill out bottom editor message. This is probably going to be different. Well, actually, it might not be different. Stuff down here, we do have length variables now. But we don't even see this stuff, so keybind's text editor, it's not even showing up right now. Is this a, yeah. We have the number of bytes to move, fill out bottom editor message. Okay, right bottom screen message, maybe that's where it's messing up. Oh, I saw it, there we go. Yeah, because this is not correct. We don't do this stuff anymore. We could call print string instead. Would that not work for doing this? Although we could set it up here if we want. We're storing. Yeah, we don't really want to do that. Message to write is an ESI, right? So why don't we just call our regular print string? We would just have to move values into cursor Y and X, I think, but that should be all right. Push D word ESI. So the message to write should be there. Just yeah, it's just cursor Y and X. Call print string and add ESP12, clean up the stack. Clean up that stack. So don't do this, don't do any of this. Just don't do any of that. Just write the thing. Assuming the length is in CX, so we'll just put message to write and SI and ESI. But but we want to move and write it at the bottom of the screen. We said that was line 67, right, in the print character and string files. So let's try doing that. Let's try moving word cursor Y 67. Let's try doing that. And then we'll do cursor X, we'll do 0. Because I'm not sure if it's set to 0 already. We'll try that. Although maybe I'll have to look up what I did in my test to make sure this works. So that's at the bottom of the screen. So we need line 66, not 67, because that's printing off the bottom, but it does look correct. So that's a good sign. Yeah, so let's do 66. We'll have to change that in print character and string as well. So let's do that also. Print character 67. Let's make that 66. And here 67. Make 66. Okay. Just debugging the editor right now. This should be the final thing we need to do. Of course, we end the video on a boring note, but there we go. We have it printing at the bottom of the screen now. We do not have the cursor printing though at the top when we're actually in. Oh, well, that did. The backspace does that. Interesting. It looks like it doesn't print by default unless we type something, and then it prints. It's not too bad. It's just kind of not great. And then that stuff, so those strings are running together and the cursor position is not right. When we go to save the file, it does save correctly, test tile 1, and then goes back. Interesting. But yeah, we got some issues there. Tried to do Control X, that didn't work. Okay, so we're back to editor. It's in the text file logic, the text editor logic rather. No, that worked. It's when we go to save file, that's where it's messing up. So save file. Right, bottom screen message. Yeah, this is not correct. These values are not right. This needs to be like, we do this inside of right bottom screen message. But I guess we're doing that for the move cursor. Yeah. Okay. This needs to be like 66. This needs to be, maybe we'll try 17. I don't know. We'll try that, I guess. We'll see what that does. Just that small change there. Test, Control S. Still running together, but the cursor is in the right place now. But we need to blank out the last line. And the previous line's right above it, which is weird. So we don't want to do that. So when we go to save, so the blank line is not working, obviously. Writing 80 blanks. Let's open this up here. We'll go to right bottom screen message. Should be at the bottom. There we go. I'm just writing a string at ESI, so I don't really need this if I'm doing that. For one thing, but the blank line is not long enough, or it's not working. And that is because blank line is, yeah, 80 blanks. So we need to either do something like this, or I don't know if that works with the times directive. I can just put a 0 right after it, and that'll be equivalent to null capping it. So that should work for the blank line. File name string is enter file name. That's null terminated as well. Although these things have spaces, I don't know if that'll count. So I'll just make sure. Make sure that everything's hugging. There we go. The keybinds, text and hex editor, I may make these null terminated also. Not sure yet. Depends how those are written to the screen and where, but we'll see if save to disk is better with this stuff here. I'm not sure. That's here as well. Editor file type, move cursor. That's okay. That's okay. Right bottom screen. When we do that, we don't need the length, so don't worry about that. Yeah. Okay. Save that. Does that look any different? Just get rid of the lengths. Get rid of the move CX length lines before we call right bottom screen message. That's all I did there. Control S. There we go. Enter file name. Test file 1. Okay, so Control R. Existing file. We shouldn't be doing that. So that is on like return from save file. We got some issues. And it was a success. We don't need that line there anymore. Keybind's text editor. Now that is not null terminated, so that makes sense. That's probably why. Also, yeah, don't need that. So we also have that in hex file, right? Save hex. Yeah, whatever. Go to save file. Save file success. That's what it was. So I'm not doing that there. The length is there. We don't need that. Okay, so keybinds, hex, and text editor. Yeah, these are not null terminated. Although if we use the length things that I put in here, then we don't need these to be. But if I'm doing right bottom screen message, I need a null terminated string. So that's what I'm doing. But sometimes it calls out this, which needs the length passed, because it puts that into there and then does more stuff. So I don't get why it printed after it did the save file though, unless these weren't null terminated. But then that won't print the file type because I'm null terminating before the file type is printed at the end of the string, right? Now that prints a text. No, that's correct. I mean, that looks correct. I saved the file. Let's do test 2, just to make sure. Test file 2. No, that's correct. It saves them there. We can even load them. It's not okay. Let's make a binary so it has .bin at the bottom. We'll do 10 AF, 1F, AF. Shift S to save, enter file, and this one's at the top because I had to make them different. Test bin FIL. No, that's correct. It's definitely, I mean, it doesn't reprint it, but I don't think it ever did to begin with. Okay, no, I think we're good. I think our printing works as it did before. I don't see any bugs. I mean, that doesn't mean bugs don't exist. They probably still are hiding just out of my reach right now. But we have sort of full parity with what we had before, just printing text to the screen, except now it is a bitmap font. And we're in an actual Vesa Bios extension graphics mode. Newer processors and machines are doing UEFI, which has, I think, GOP, general something, or graphics object protocol. I don't know, whatever it is. They have different ways of doing this with UEFI, but this is still old school 1998 style Vesa Bios extensions. But we got this working now. So going forward, we can do graphics things. We can write lines, triangles, shapes, walls, vector graphics, games, do whatever. I mean, anything you want with graphics we can do now. A windowing system, if I can get the mouse working somehow and make different tiling window manager. I don't know. We can do whatever. The world is your oyster. If you have any suggestions on what you want to see next, please let me know. I'll think of some things. I might fix up some stuff. I might fix up the editors, make sure they work going forward, actually fix up the bugs we still have. And then write like some basic programming languages in machine code or assembly or something within our operating system, or I have other stuff I can do. So I'll think of some things, but if you have anything you want to see, let me know, please. If this text is too small, let me know. I can make a bigger text, right? I will have the source code for this OS as it stands right now. So at the end of this video, not at the start, but as of the end of this video right now, this source code, the OS build, I will have inside of a Git repo. That link will be in the description if you want to look at the end result and mess with it, right? So, but yeah, just let me know if you want to see anything specific. Thank you for watching. I really do appreciate it. And yeah, I will see you on the next one.